Hello and welcome to today's central exercise session. This central exercise session for sheet number 13 will be pre-recorded because we will not have the chance to meet for a regular central exercise session about that sheet anymore. And I still want to show you some examples regarding the topics of that last week, which is integration. If you have any questions about that sheet, I will unfortunately not be able to answer them live. But of course, you're welcome to ask your questions either on the Moodle forums or also on the usual chat channels. I will try to answer all of your questions there. So let's start with the first problem of today's session, which is 13.1. Now, as I've said already, the questions on this sheet all revolve around the general topic of integration. We'd start with an application of integration, which is computing the area. Now, you remember that we motivated integration through computing the area below the graph of a function, or more precisely, the area between the graph of a function and the x-axis. And that area could be positive or negative depending on whether the graph was above or below the x-axis. Of course, you can also use this to compute the area enclosed between two graphs, and that is exactly what we're going to do in this problem set here. So there's two functions. They're called f and g, both mapped from the reals to the reals. F is defined as x to the power of 4 minus 5x squared plus 4. G is defined as minus 9x squared plus 9. And the task here is to determine the intersection points of those two graphs and the area enclosed between the curves inside of these intersection points. To give you a rough idea of how those functions look, I'll make a very rough sketch before we start, but just let you know that will not be necessary to solve the problem. So we'll do without the sketch, but it helps to have a rough idea of what we're talking about here. So if you can, without losing too much time, a sketch is probably not a bad idea, but you don't have to do it unless the problem statement explicitly asks for that, of course. So again, roughly, those two functions look like this. I'll start with a sketch of the function f. So f looks like that here. That is the function f. And the function g, similar to that one, that looks like this here. So that's the function g. And that means the area that we're talking about is this area here. That's the area that we want to compute. Now, how do we go about that? Well, as the problem statement suggests, the first thing to do is compute the intersection points. So we'll start with that. So in other words, what we want to do is we want to compute the roots of f minus g. And if we look at that, f of x minus g of x is, well, f is x to the power of 4 minus 5x squared plus 4, and g is minus 9x squared plus 9, so if you subtract g, and that's plus 9x squared minus 9, of course. So what we get is x to the power of 4, then we have plus 4x squared, we have minus 5 plus 9, And here we have 4 minus 9, so that's minus 5. Now to get the roots of that expression, we can just make a simple substitution. We substitute y for x squared, and then this translates into y squared plus 4y minus 5 equals 0. The roots of this can easily be computed. So the two roots here for y are minus 4 plus minus the square root of 4 squared, that is 16, minus 4 times 1 times minus 5, so 4 times 5 is 20, we get plus 20. And we divide that by 2. So we have minus 4, here we have the square root of 36, the square root of 36 is 6. So it's 4 plus minus 6 over 2, or minus 2 plus minus 3. Or we get the two solutions, plus 1 and minus 5. So that's the two possible roots in terms of y. Now remember, y was equal to x squared, so y cannot be negative. And that means minus 5 can be excluded for the problem at hand. So in other words, x squared is 1, and that means x is either minus 1 or plus 1. So we get the two intersection points. The first is minus 1, and if you compute the value of the graph at minus 1, then you get for g, for example, you get minus 9 times 1 squared plus 9, so that's 0. And of course the same is true for f. So the point is minus 1, 0. And for 1, again, the function value of g at 1 is 0. You can just compute that. So that is the two intersection points that we were looking for. So if you look back at that sketch here, then that means these points here, those are the points minus 1, 0, and 1, 0. That's the two intersection points. The next thing we want to know is we want to compute the area between those two. And of course, there's only these two intersection points. So between the two intersection points, either g is above f or f is above g. But of course, we'd like to know which one it is. So we just check that very quickly, for example, by computing a value of the two functions. The easiest choice would probably be 0. So let's compute this value and this value to see which of the two graphs is higher. So if we do that, as f of 0, well, f of 0, that is equal to plus 4. And g of 0, that is equal to plus 9. G is therefore above f in this interval from minus 1 to 1. And that means the area between those two graphs can be computed by the integral over g minus f. So the area is equal to the integral from minus 1 to 1, g of x minus f of x dx. Now we just have to do the computations here. G of x minus f of x, remember how those look like. So what we get here is the integral from minus 1 to 1. G of x was minus 9x squared plus 9. F was x to the power of 4, so minus x to the power of 4, minus 5x squared, and we have to change that to a plus because we're subtracting, and plus 4, that changes into a minus here. So this is the function that we need to integrate. And let's first simplify that a little. So we have this x to the power of 4 minus x to the power of 4. We have minus 9x squared and plus 5x squared, so that's a minus 4x squared. And finally we have 9 minus 4, that's a plus 5 then. So this is the expression we need to integrate. And using the usual integration rules that we know from the lecture, we know this is integrated as minus x to the power of 5 over 5 minus 4x to the power of 3 over 3 plus 5x, and the boundaries are minus 1 and 1. Now we just evaluate that, and we get minus 1 over 5 minus 4 over 3 plus 5, and then minus, the lower bound is minus 1, so that's 1 over 5 plus 4 over 3 minus 5. So altogether, if we add this up, the result that we get would be 104 over 15. That is the area that we're looking for. So this completes this discussion of C13.1. So let's go on with C13.2, the next problem on our sheet. That is a problem about two very important integration techniques that you learn about. The first is substitution, integration by substitution. The second is integration by parts. And we're going to demonstrate both of these using an example. The example for substitution is in part A, the indefinite integral of x squared times the sine of x to the third plus 2 dx. Now for substitution, we need to find a suitable substitution first, and that is the difficult part about this. Once you know the suitable substitution, mostly you will be fine, but it may be hard to guess that substitution. One good start is usually to look for complicated functions like the sine or the logarithm that have an argument that is not just x or a multiple of x. So here we have this sine function, which has an argument x to the third plus 2. So that's not just x or a multiple of x. And that's always a good candidate for trying a substitution. Now let's see if we can solve the integral using this substitution. So we try the substitution. Let's call the new variable z. Z is defined as x to the power of 3 plus 2. Then you will remember the formal rules that you had to go through for that substitution. You first differentiate that expression dz by dx. So that is 3x squared. And then you solve that for dx. So formally, dx is then dz over 3x squared. And now we try to solve the integral using this expression here. So once again, we want to solve this integral up here. Let's copy that. And then using this substitution, we get the integral over x squared times the sine of, and here our new variable comes in, so that is z, that's how we defined it, times, and then instead of the dx here, we write dz over 3x squared. And as you can see now, this x squared here appears here and here. That nicely enough cancels out. and that's exactly what we want of that substitution. Of course, we want to have an expression that only uses the new variable, only uses z, otherwise we cannot integrate it. And nicely enough, the x squared, the complicated part, cancels out. So we're left with 1/3 sine z dz. That's an expression that we can integrate. So that's simply 1/3 times the negative cosine of z plus some constant. And then, of course, we have to undo the substitution. So instead of this z here, we now write the original expression. So that's minus 1/3 cosine of x to the power of 3 plus 2. And again, plus some constant c in r. So for the indefinite integrals, please always add that constant, indicating that every translation of that function would also be an antiderivative. Of course, if you had boundaries here, so if the integral was not an indefinite one, but a definite one with boundaries here, then you would also just apply the substitution to the boundaries as an alternative. You could either use that approach and then undo the substitution at the end and then insert the original boundaries, or you could translate the boundaries and insert the translated boundaries right here. We'll see an example of that in 13.3 later on, so I'm not going to elaborate on that by now. Instead, let's have a look at part B. Part B is an example of integration by parts. And in this simple example, we integrate the function sine x squared dx using integration by parts. Now, the idea of integration by parts is to represent the integrand as a product of two functions. And integration by parts simplifies this expression by integrating one of those and differentiating the other. And of course, you have to choose those wisely so that the new integral is actually easier or straightforwardly solvable, and not as complex, as complicated as the old one. There's also another option that's exactly what we'd be doing here. The integral, the old integral, might reappear, but possibly with a different constant or a different sign in front of it. And that will allow us to solve for this integral. Let me demonstrate how this works in this context. So first thing we do is we rewrite the integral with an integrand that is actually a product. And one way to write this here is, this is the sine of x times the sine of x. Now we use this, one of these functions as f prime and one will be g. As an advice for the exam, you should always indicate something like this, f prime g or whatever you want to use here, so that the corrector knows what your intentions were. Right? That signifies you were going to do integration by parts and you were going to use this as f prime and this as g. And even if you make an error in the next step, maybe you can still get some credits for at least having the correct idea here. Now, let's do integration by parts. What we do here is we first integrate f and then multiply this integrated f prime by g, right? So the integral of sine x is the negative cosine. That means we have negative cosine of x, and the sign just stays here. So what we do is we write the product of f times g, and then we subtract an integral, and that is now the integral over f times g prime. So f prime is integrated and g is differentiated to get the new integral. Now the integrand of the sine x, we just computed that. That was the negative cosine. and the derivative of the sine is the cosine, the positive cosine, so g prime is the positive cosine. So that's the new integral that we get. And now we're going to apply a little trick. Let's first copy that first part here, cosine of x times sine of x. So what we have here is, we can take out that minus, and then we're left with the integral over cosine of x squared dx. And that's similar to what we started with, but not quite the same. So let's do a little reformulation here. And as you know, the cosine squared plus the sine squared equals 1. Or in other words, the cosine squared is 1 minus the sine squared. We're going to use that relation right now to express this integral. And then we can rewrite this as minus cosine times sine plus the integral over 1 dx minus the integral over sine of x squared dx. And of course that integral over 1, that is easily computed. That's just x. And now if you look at that result, you will notice that this integral here is exactly the one that we started with. Here it is. So what we now have is an equation for that integral that says this integral over sine x squared dx is equal to minus cosine x sine x plus x minus, again, that same integral. So we can just solve that for this orange expression to get the value of the integral that we're looking for. So this is then given by taking the integral to the left and then dividing by 2. That's what we need to do here. So this is 1/2 minus cosine x sine x plus x. Or in other words, let's rearrange that a little, x over 2 minus 1/2 cosine x sine x. So that's the result of this integration using integration by parts. And of course, it's not necessary that the integrals reappear and you solve possibly. It could also be that the resulting integral after integration by parts, now this one here, or maybe after several steps of this integration by parts, the remaining integrals would become easier and easier, and sometimes you will hopefully reach a point where you can just solve that remaining integral. There's a lot of other example problems on the exercise sheet 13 for the homework problems, and of course you've got the solutions to this on the Moodle page. So my advice is, as usual, practice that using the examples that we have provided on the exercise sheet. Now that completes 13.2, where we have a look at substitution and integration by parts as useful integration techniques. Now the last central exercise problem on that sheet 13 is our exercise C13.3, and we'll tackle that one right now. This looks a little more complicated, but it actually is not. So what we are given here is first a positive number t, a function f that is defined on an interval from 0 to t and maps to R. It's continuous and it has the property f of x plus f of t minus x is not 0 for all x. And the first part of this problem is to show that certain integration holds, and that is the integral from 0 to t, so over the whole interval, of not of the function f, but of the following function, f of x over f of x plus f of x, f of t minus x dx, that is t over 2. And the question is, how can we prove that? So again, the t is a constant here. That's a parameter that we choose up front here. And then for every function with that property, this will work. And that property is mainly important because the denominator here, that's exactly the denominator, that of course may not be 0. Now, let's see what we can do here to prove that integration here. What we'll do is we'll use a substitution. I'm going to use a very simple one. Again, inspired by the argument of the function f here, we use the substitution z equals t minus x. So then dz over dx is minus 1, and that means dx is minus dz. Also, we can easily solve that substitution for x. And that is, x is then simply t minus z. And using this, we can now rewrite the integral the following way. So this original integral here using the substitution, we can write this as, well, let's first keep the x's inside. That's f of x over f of x plus f of, well, here's a z, right? And then we also get this here, so instead of dx we write minus 1 times dz. And of course we also have to take care for the boundaries here. So if we use the substitution for the boundaries, then for 0 we just substitute 0 in here. Instead of x we get t minus 0. So that's t minus 0 here. And for the upper bound, for t, we get t minus t. So again, we take this t and we substitute it here for x. So what do we get? Well, this is the integral from t to 0 then. We still have these x's in there, and we don't seem to easily get rid of those. So if they don't cancel out, then the other possibility is to use this substitution, solve for x, and then use that. So we can replace every x with this z expression here, t minus z. And we do just that. So that means we use this here instead of x. And we also have that minus here. Let's take the minus in front of the integral. So this is how this looks now. And finally, one last step. You know that we can just reverse these integration bounds. So we can exchange upper and lower bound. And what that does is it changes the sign of the integral. So if we do that, then this minus here will become a plus. So this is the same as the integral from 0 to t f of t minus z over f of t minus z plus f of z. And somewhere I mixed up that denominator, right? I'm sorry. So that, of course, that should be a plus everywhere. Dz. Okay, now what have we gained by this? Not a lot, right? So this here looks almost the same as this. In fact, even more complicated, right? We have this t minus z twice. Here we only had that once. But what we have gained is the knowledge that the value of this integral and this integral is exactly the same. So that's the interesting point here. The value of this and of this is equal. So these two have the same value. And that means, well, we can just try to add them and see what happens. So we add the two blue integrals. What do we get? Well, the first one is the integral from 0 to t, f of x over f of x plus f of t minus x dx. And the second one is the integral from 0 to t, f of t minus z, f of t minus z plus f of z dz. Now we can do that, and of course the name of the integration variable in here is actually totally irrelevant. Whether we call this z or x does not change the value of the integral a bit. So to be more consistent, we could just rename that. We let the first one use x, and then the second one we rename that to x as well. So we kind of forget the relation between z and x. We took care of that substitution by changing the bounds of the integral accordingly, so we don't really have to remember what we did there anymore. And now you can see we can take these two integrals and write them as one. Yeah, they both use the same variable name, they both use the same bounds, so we can just write this as one large integral from 0 to t. You can also see that the denominator is absolutely the same. So that means we get f of x plus f of t minus x over f of x plus f of t minus x dx. And now this expression here, well, that's just 1. And now you can see where this is all going. The integral of 1, that's easy to solve, right? The integral over 1, that is just x from 0 to t, and of course if we evaluate that, what we get is t. So in other words, the sum of these two integrals is t. We have already stated that these two integrals have the same value, so each of those summands contributes exactly half of that value. And that means the integral of one of these, f of x over f of x plus f of t minus x dx from 0 to t, this integral is simply t over 2. And that's exactly what we had to prove. So this completes the first part of this problem C33. Now the second part is just a simple application of that. We want to compute an integral involving sine and cosine. And the one thing that we need to use here is a relation between those two. Now the cosine of x, that can be written as a sine. If you have a look at those two functions, you remember the cosine is basically the function that looks like this here. Whereas, oh, that's the cosine here. Whereas the sine looks like this. Have to get those in sync. Yeah, Yeah, so that's the sine. And as you can hopefully see, the cosine is exactly the same as the sine, but it's translated, yeah, along the x-axis. And the translation can be written as, that's the sine of pi over 2 minus x, right? So pi over 2, that is this root here of the cosine. So if you translate the sine by the right amount, then you get exactly this expression here. Okay, so let's try to finish that. So let's try to compute the integral that we have in the problem statement. Now that integral is the integral from 0 to pi over 2 sine of x over sine of x plus cosine of x dx. And as you can also see in this interval from 0 to 2, the sum of sine of x and cosine of x, of course, is over 0. So if you look at this interval here, then you'll see that sine of x plus cosine of x is greater than 0 everywhere on that interval. So the denominator here is not a problem for us. And furthermore, we can rewrite that integral in the form required by A, and that is sine of x over sine of x plus the sine of pi over 2 minus x dx. And that's exactly the form that we needed in part A, f of x over f of x plus f of t minus x, and t is now pi over 2. So this here is our t. And now with the result from part A, we know that this integral is exactly t over 2. So with t being pi over 2, we get pi over 2 over 2, or pi over 4. And that gives us an easy way to solve this specific integral. Now, of course, that only works for very specific integrals or for very specific functions, but the trigonometric functions are a good example of functions where we can use a relation like that to compute seemingly complicated integrals. Well, that completes 13.3, and that's the last central exercise problem on that sheet. For the homework problems, you will have noticed most of those also revolve around integration. There's one 13.4 explicitly, that's more or less an addition to sheet number 12. By popular request, I added a question about Taylor series and convergence of Taylor series. If you have done the test drive exam on TUM exam, you will note that this, or part of this problem here, was one of the problems on that test drive exam. People asked for solutions to that. So here is the problem once again, and also, of course, you get a solution for that. There's a little twist to that. The test drive exam only asked for convergence of the Taylor series. Of course, the real interesting question is, if the series converges, does it converge to the original function? And that's the last subproblem that I added in this homework 13.4. For that, you'll usually have to deal with the remainder formula. And that's exactly what we're going to do in that homework. So have a look at the solution if you want to have one more example of Taylor series, convergence of Taylor series, and dealing with this remainder formula. Now that completes this central exercise class. As I said, if you have any questions, don't hesitate to ask on the forums or on the CE chat. We'll try to answer all of your questions there. And of course, you're also invited to join us for the tutorials. The last tutorials of this semester will take place this Thursday online on Zoom, and you're welcome to ask any questions you might have there. If I don't see you at the tutorials, let me take this opportunity to wish you all the best for the exam. At least virtually, I'll meet you at the exam in one way or the other. So all the best for the exam. I hope you succeed. And of course, I always hope to see you in the upcoming semester when we talk about multi-dimensional analysis and many, many more interesting things to come. Also integration over multivariate functions. So that's going to be one of the most prominent topics then. So again, all the best for the exam. Enjoy your semester break. I hope you get to have a semester break, at least a little bit, to relax, to enjoy some time off from the exhausting semester. And I hope to see you in the upcoming summer semester.